So, good morning, students. My voice is audible to you?
Yes, sir.
Okay, fine. So, in our last lecture, we discussed about asymptotic notations, right? So, today we also discuss asymptotic notation, so you all can understand what actually they are, how we can use, right? What the purpose of that graph, right? All the understanding how we can do, right? So, for that, I'm going to share a whiteboard. My voice is not audible, Vishwajit. Check your headset. So asymptotic notations, right? So the first asymptotic notation is that big O. Big O notation. And we are going to represent like O. Alright, asymptotic notations. The first one we have big O. So big O. We are going to define this big O with O. O symbol, right? So what is asymptotic notation? Asymptotic notations are basically the way with the help of that we are able to analyze our algorithms. What way? A mathematical way, right? We have a mathematical way. With the help of that, we are able to analyze our algorithms. If I'm talking about this, let's suppose this is my graph, and here we have one constant Cn. Here is like this is my k, or we can define with any symbol, right? And this is my n. If one condition is going to understand, you all can understand each and every point. It is not like that this line is always like in a downwards. It may be like in this side also, right? So it's not like this. Always it's on a downside. Let me create this. So now this is our, now what thing is that, what is this point, right? I'm going to highlight this. What is Cn? What is Fn? So now let's suppose we have one condition, Fn function we have equals to and we can say big O of GN. We have one like this. And what is GN? We can say big O. We can also write like this. Fn less than equals to Fn less than equals to, this is for C dot Gn, right? So Cn is basically a constant. This is the constant term, right? Which shows in this big O notation, like if when Cn is going to increase, we need to find that point, right? Maximum time, maximum value it is going to choose, or we can say greater upper bound condition. What is that condition? When this is going to separate, this condition is going to true. Let's suppose one condition I am going to share here, and one more thing, C is greater than 0. These are few notations. N is greater than equals to K. I will let you know each and every point, and K must greater than 0, right? Now, the next thing we have here, let's suppose Fn equals 2n power 2, right? Plus n. The same example I am going to cover. Now here, Fn is given. And what we are going to check, which value is going to check, hit and trial method we are going to use here, right? Hit and trial method we are going to use here. And here we have, if this function is less than equals to, we can say C dot n square. What is the complexity for this equation? N square. We are going to pick n square. Why so? Because we have already defined here 2n power of 2. That's why this. So gn is n square. Till now, any doubt about gn? We are supposing, and actually we have, if we have this condition, for this complexity maximum time it takes n square, right? N is also part of this. So now when this condition is going to true, yes, what value we are going to assume here? Let's suppose if I am going to take a value 10, 10 square, let's suppose 5 is very 25. If I'm going to take value of n is 25 into 2, it becomes 50. So this becomes 50 plus 5. Here we have, just a minute. Yes, Nitish. Yes, students, if students are not able to join, informed me after the lecture, right? Like right now, if I'm going to share my screen to you, you all can see here students are not able to join, right? So this thing happened sometimes. Clear? So you all can update me on WhatsApp if you are not able to join. There is some technical issue. Now, n square is 25. What value we can assume for C? So this condition becomes true. 3, if I'm going to pick 2, then again it is going to less than. But if I'm going to pick 3 into 25, it becomes 75. So after 3 value, we can say that here the always Cn becomes greater. Cgn becomes greater. This part always. So this is the point. This is the point where, so this is the K point. After that, there is no, sometimes like this graph shows that this area, let me circle here, this area shows that sometime both the points are equal, sometimes condition is going to more, then again less, but at certain time, at certain point, they are not able to cross. So that is a K point. Clear? So this is a point. After that, we can say it takes maximum time. If the system is going to take maximum time, then big O is going to give a worst case. Clear? Yes, students, let me through chat if it is clear to you or not. Yes, students, tell me. Now students have joined. Yeah. Due to internet issue, each and every time a connection is going to break, right, students? So I asked about this graph about big O. That is clear to you or not? About big O. Voice is audible, students? Yes, students. Voice is over. Okay. Okay, fine. Big O is clear to everyone. Even now, I am going to share a notepad to write few conditions. So now here we have second is big omega. Here is the omega symbol. This is the omega symbol, right? That is visible. So this is the omega symbol for that. And second, for this again, the graph is same, but now this time Fn, here we have Cn or Cgn we can say. So here we have again Fn, that is the value of Fn is 2n square plus n greater than equals to Cgn, right? Cgn. So in previous big O, in big O we have 2n square plus n less than equals to Cn square, right? This is the condition. At what time this condition is going to true? When the value of Cn is 3. Value of Cn is 3. Let's suppose if n is the value of n is 5 at C point. At C point, we can say this becomes 75. This becomes 75 and this becomes 55. So this condition executes. This is a part of big O. But here we have when this condition is going to true. This condition true till the value of C is 2. But when we have 3, so big omega is going to give best case. Big omega is going to give best case. This Fn is going to true, means greater than, till when C, the value of C is 2. Like again, I am taking the example of this n square, right? Here we have 2 into 5, 55, to 55 plus 5, right? Greater than equals to, here we have 50. So big omega is for lower bound, the lowest condition. That is the last condition. After that, we can say this point is going to change. So this omega is going to give best case, best case, best case values. So this is also for lower bound, which is the least greatest lower bound, greatest lower bound we can say. Clear? Yes, students, clear? If both the things are clear, just let me know. For big O, we are going to find lowest. So here we have lower bound greatest in big O. we have find lowest upper bound. So this is the maximum value, or we can say this is the maximum value. After that, Cn is going to greater, and this is the point. After that, this condition becomes lower. Both are reverse. Yes, students, tell me if any doubt, any query, you can discuss. So last one is theta. The third one is theta. And the symbol is theta. And this is going to give average. This is for average case. This is for average case. How? Here we have one more line. We can say like this, C1 and C2n. So the conditions are like C1 of n less than equals to Fn, or that is less than equals to C2 of n. Clear? So what it means? So this is the part. Let me mark. So this is the area is for, it is going to tell you the maximum value, and this area is going to tell you the last point, lower bound, greatest lower bound. After this, if we are exceeding one point, that is going to change the value. Below that value, below that value, this condition is going to evaluate always true. But at that point, this condition is going to reverse, right? So one is, that's why this is going to give the average. So between 2 less than Fn, Fn is greater than 2, or it's less than equals to 3. So these are the 2 points, 2 C values we found here, right, to evaluate our this equation. It's clear now? Yes, students, let me know if any doubt, any query.
No doubt, sir.
Okay, fine. So I'm moving to the next, a very important and related to this. We have a few properties we are going to discuss, right? Few properties are like, the first one is reflexive. Reflexive. Another one is symmetric, and the last one is transitive. Transitive property. ठीक है, right? So next is for big O, for omega, big O, for omega, for theta, little o, little omega, right? These are the five. I'm going to write here big O, big O. Second one is uh, big omega. Third one is theta, and the fourth one is little o. Fifth one is little omega, right? These are the five. What is the difference between, first we are going to discuss what is the difference between little o and big O. In little o, in big O, we are going to write our condition like this: 2n square plus n less than equals to cn square, right? And in big omega, the condition is going to reverse, greater than equals to. But in little o, equal part is going to remove. In little o, we will write here 2n square plus n less than. Only the difference is that equals to. In same way for little omega, 2n square plus n greater than cn square. Clear? First of all, difference is clear to everyone. So we need to check which one is reflexive property, which one is transitive, and which one is symmetric. So the thing is that if we have any condition, let's suppose suppose this becomes A, this whole condition A, and this whole condition becomes B. This is B, right? If A is less than equals to B, this condition is going to happen, right? Then we can say this is reflexive. And for greater than, we can also say this is reflexive. Greater than equals to, again equals to. For theta, we have A less than equals to Fn, right? Let's suppose, and again this less than equals to B, again equals to, then this property is also evaluated. Clear? So in little o and big O, no. Little o and omega, reflexive property is not, because equals to is not there. Clear? If we have a equals to sign, then we can say this is symmetric, this is, and this is also. Sorry, not for this. Let me. This is for. Yeah. Symmetric means we are going to find that point where condition is going to change. Means average case. So average case is only occurred in symmetric, in theta. So there is no symmetric property, no symmetric property. Also there is no symmetric property, there is no symmetric property here. right? And transitive, what about transitive means? Transitive property is like if A is less than equals to B, right? And again B is less than equals to C. So we can say A less than equals to C. This we already proved in mathematics, transitive property. We just using this thing. Let's suppose we have one condition. This is F1, and same way we have another F1, F2 that is less than equals to C of Hn. C of Hn. This we supposed this is C of Gn, right? For F, this is for Gn. F2 is for Hn. So if F1 is less than for Cn, means A and B is less than for this, then we can say transitive property, right? And so here we have this property also, this in this case also transitive property. Or if equals to is not there, we can also suppose this thing. If A less than B and B less than C, again we can say A is less than C for little o, for little omega. So all the five properties are present in as a transitive. A very important and easily you can understand now. In reflexive, if equals to is there, then we can say reflexive. In little o, little omega equals to is not there, then we can say this is not the reflexive property. But if we have a symmetric, only the average case is going to tell the symmetric property. And for transitive, this property is going to be A is less than B or A is greater than B. In same way, for little omega, so big omega, we can say A is greater than B, B is greater than C. So we can say A is greater than C, right? Equals to is same in a reverse case. So both the case are true. All the five cases are true in transitive. Yes, students, clear now?
Yes, sir.
Now you all are able to understand about this asymptotic, how we can check what the things we need to select. Now the next, when this lecture is till 1 p.m. 12, right? We have left, yes, 12. Now about time complexity. Time complexity is basically is going to tell you only 3 minutes are left. Just recall all the things, right? That's why, right? This topic we will cover in next lecture or after joining of your in. I need actually 20 to 30 minutes to explain all the things, all the time complexities of all the algorithms, all are going to attend that lecture. It's a very important. In a single lecture, you are able to find all the time complexities of all the algorithms, maximum algorithms which we can cover, right? So, and we can say the order of time complexity we also discuss in next lecture. If you have any doubt in this session, you can discuss. We have just 2 or 3 minutes left. And all the students who joined late, make sure you have attended the 30 minutes of lecture, because some students are joined very late.